everyone. In this video, we will be talking about covariance and correlation as a way to describe the relationship between two random variables. So we'll start by defining the covariance and then introduce a corollary to covariance, the correlation. So let's talk about the covariance first. We can think of modeling the dependence between two random variables, so how one changes depending on the other. For example, as y1 tends to increase, perhaps y2 tends to decrease or tends to increase as well. We've got two ways that we can measure this relationship, the covariance and the correlation. So let's start by defining the covariance. We say that the covariance between two random variables, y1 and y2, is the expected value of y1 minus mu1 quantity times the quantity y2 minus mu2. Here the mu represents the mean of each of these. This is very similar to our definition of the variance being the expected value of y minus mu quantity squared. Here, instead of having y minus mu squared, we have y1 minus mu1 times y2 minus mu2. The larger the absolute value of the covariance gets, the greater the linear dependence between y1 and y2, so the stronger that relationship turns out to be. If we have a positive covariance, that suggests that as y1 tends to increase, y2 also tends to increase. If we have a negative covariance, that suggests that as y1 tends to increase, y2 tends to decrease. Now, if we have a zero covariance, then we say that these random variables are uncorrelated. Now, covariance, unfortunately, cannot be used as an absolute measure of dependence. The reason for that is that the covariance depends on the units. If the random variables y1 and y2 tend to take on large values, say, for example, income levels, then we'll have a large relative value of the covariance. However, if y1 and y2 tend to take on small values, say diameter of a cell in nanometers, then we will have small values for the covariance. So we're looking at a very scale relative measure. One solution to get around this is to standardize the covariance, and here's how we do that. We'll standardize the covariance by dividing by the standard deviation of variable 1 times the standard deviation of variable 2. Here denoted sigma, not sigma squared like the variance. What this gives us is the correlation coefficient, which we will denote as rho. Now this correlation is probably very similar to a correlation that you learned about in Stat 101 because this is the correlation. This is how it's defined mathematically. So your interpretation would remain the same as a previous Intro Stats course. The sign of this correlation coefficient will be the same as the sign of the covariance. Why? Because standard deviations are guaranteed to be positive. If we have a correlation that is equal to 1 in terms of the absolute value, this indicates perfect correlation. So all variables or all observations y1 and y2 fall on a straight line, and so on. So let's take a look at a result here. It turns out that we have a similar result to our computational variance formula in terms of a computational covariance formula. Specifically, we can find the covariance between random variables 1 and 2 as the expected value of y1 times y2 minus the expected value of y1 times the expected value of y2. So let's prove this result. We'll start with the definition of covariance, which is the expected value of the quantity y1 minus mu1 times y2 minus mu2. We'll distribute those quantities, so we get the expected value of y1 times y2 minus mu1 times y2 minus mu2 times y1 plus mu1 mu2. These mu's, again, are representing the means of y1 and y2, so we can treat these like constants and pull them out of the expectations. So we get the expected value of y1, y2 minus mu1 times the expected value of y2 minus mu2 times the expected value of y1 plus mu1, mu2. We'll then take those expected values that are individual. So we'll take the expected value of y2, which we've defined to be mu2, expected value of y1, which we've defined to be mu1. We get something that looks like this, and then combining like terms, we end up with our computational form of this variance or covariance. So let's think back to a previous example. We're looking at the amount of gasoline that is stocked and sold in a tank. We'd like to find the covariance here. So our joint PDF is 3y1, where 0 is less than y2, is less than y1, is less than 1. In order to find the covariance, there are three pieces that we'll need. We'll need the expected value of y1 times y2. We'll need the expected value of y1 alone and the expected value of y2 alone. We'll go through this integral fairly quickly. To find the expected value of y1 and y2, we'll take y1, y2 times the joint PDF. We'll integrate through. Here I've integrated with respect to y2 first, followed by y1. We get 3/10 for our expected value of y1 times y2. Now we'll find the expected value of y1 and y2 alone in a similar way. So the expected value of y1 is 3/4. Similarly, the expected value of y2 is 3/8 or half of y1. So then our covariance becomes 3/10 minus 3/4 times 3/8, 4.01875. So this is our covariance. Again, this seems like a small value, but remember that that covariance is relative. It depends on the scale. Here, because all of our values are bounded between 0 and 1, that covariance should be a small proportional value as well. So we have a theorem here, and this theorem's important because of the way that it is stated. So if y1 and y2 are independent random variables, then the covariance of y1 and y2 must be 0. In other words, independent random variables must be uncorrelated. Here's what I want you to pick up about this theorem. It does not go both ways. Covariance of 0 does not imply independence. However, independence does imply that the covariance is equal to 0. To see why this doesn't work in both directions, let's take a look at an example. Let's let y1 and y2 be two discrete random variables with joint probability distribution as shown in the table below. Now let's show that these are dependent variables but have 0 covariance. Well, how do we show dependence? Well, we can look for a violation of the multiplication rule. There's a fairly obvious one in the center of this. Take a look at the probability that y1, sorry, this is a typo here. These should all be y1, so that y1 is equal to 0 and that y2 is equal to 0. Well, that's 0. If we were to find these marginal probabilities, so the marginal probability that y1 is equal to 0 is 6/16. Marginal probability that y2 is equal to 0 is also 6/16. 6/16 times 6/16 is not 0. So there is our obvious violation here. Now, we can find the covariance by hand. However, what I'd like to do is actually show you a way that you could do this using something like R. So here I'm using a function from the tidyverse in R called tribble. And what this tribble function does is allow you to specify essentially a data set like you would a table. So this data set that I'm writing, it's a pretty short data set. It's actually just the table copied over. Has 3 columns, y1, y2, and the probability. So for example here, the probability that y1 is -1 and that y2 is -2 is 1/16. So this data now has my probability table written in an R understandable form. Now here's what I'd like to do. Because this is a discrete random variable, we can calculate expected values by taking the sum of the function that we'd like to get the expected value of times the probability. So here I can do this directly by taking advantage of operations in R. So I'm going to take this data and I'm going to calculate 3 summaries. I'm going to calculate the expected value of y1 times y2, that's this first row here, by taking the sum of y1 times y2 times the probability. I'll take the expected value of y1 by taking the sum of y1 times the probabilities, expected value of y2 as the sum of y2 times the probabilities. So my expected value of y1 is 0, my expected value of y2 is 0, and my expected value of the product is also 0. This means that the covariance will be 0. So here we have an example where we do not have independence, but we still have 0 covariance. In the next video, we will talk about some additional useful tools that we can use to find expected values of linear functions. I'll see you there.